Okay, today we're going to talk about what are called vector-valued functions. Okay, you're used to, in calculus, doing functions that are called real-valued functions. Let me write this down for you. A real-valued function is one where you plug in a number and you get out a number. Okay? Such as, an example here would be f of x equals x squared. Okay? A vector-valued function is a function where you plug in a number and you get out a vector. So an example of that might be something like this. I can write f of x equals, and maybe you would get a vector like 5x comma x squared. Okay? Now, a couple of things. Because f of x is a vector, I should put an arrow over it. The arrow normally just goes over the f part. Okay? And another thing is that when we do vector-valued functions, for the independent variable, we usually don't use an x. We oftentimes use a t instead. Okay? You could also have, so that one right there that I drew is a two-dimensional vector-valued function. You can also have a three-dimensional vector-valued function. Okay? All right, now, there's something you have to be a little bit careful about when it comes to graphing. Okay? Let's write this. Suppose r of t equals the vector t squared, comma, t squared plus t minus 1. Okay? So if I said graph r of negative 2. Okay, let's do that. R of negative 2 would be the vector negative 2 squared, comma, negative 2 squared plus negative 2 minus 1, and so that is the vector for 1. So let's graph that. And there you see the picture of the vector r of negative 2. Okay, now, suppose we have a question B that says graph the function r. Okay, graph the whole function. There's a problem that we would run into, which is this. if we drew all the vectors, here's what we would end up with. Something like this. Well, here's what r of -2 looks like. Okay, so that's fine. But there's a bunch of other vectors as well. We would get something like this. This is going to take a few minutes. I'm going to draw a whole bunch of vectors here. You kind of seeing what's happening? Okay, I'm going to skip ahead now. Okay, you see the problem we end up with? The vectors themselves, they overlap each other so much that you just end up with this big red blob. And you can't see any individual vectors at all. Okay, that's the problem you run into when you try to graph a whole bunch of vectors. So what we do to get around that problem, when you want to graph 1 or 2 or even, let's say, 5 values of a vector valued function, then you can just graph those 1 or 2 or 5 vectors. But if you want to graph all of the values of a vector valued function, then what we would normally do is just graph the terminal points of the vectors, and so you would end up with something more like this. Okay, and let me show you an actual computer drawn picture of that. Okay, so you see that there? So the red vector is one vector, r of -2. The blue parabola type shape is a graph of the whole function. They're graphing all of the vectors, but the problem is that the vectors overlap each other, and so all they're doing is plotting the terminal points of each vector. Okay? And then that draws out a path in space. And so what we're actually doing here is technically not anything different than parametric equations. Here's a new example. R of t is the vector t cubed minus t, comma, 1 over t squared plus 1. And you see right here they've graphed the vector r of 2. Here they've graphed the vector r of -1. There's nothing special about those two vectors. They just said, let me show you a couple of examples, is what they've said. And they've shown us r of 2 and they've shown us r of -1. Okay, but this blue, which looks black once I highlight it, but this blue curve right there, that's the terminal points of all of the vectors of the function. So that blue graph is the entire graph of the function. If we put in all of the red vectors pointing to all of those blue points, then it would just be one big red blob and you wouldn't even be able to tell what the shape is. Okay, here's an example of one in 3 dimensions. R of t equals the vector cosine t, comma, sine t, comma, t, where t goes from 0 to 4 pi. And you see what you get is a spiral. Well, they've drawn one of the vectors as an example of one vector, r of 7 pi over 4, that's drawn in red. And then to graph the whole function, they've drawn in blue the terminal points of all of the vectors. Okay? And you should try to get yourself used to, understanding why does that come out to be a spiral? Because you have here the x coordinate is cosine t and the y coordinate is sine t. So in the x and y directions, you have something that's going to be circular, but as it goes around the circle, the z component is t. So as it goes around the circle, the height is going to get higher and higher, and so you end up with a spiral. Okay, let's look at this one. Here we have two vector valued functions, okay? We'll call them R1 and R2. Okay, so the first one, R1, gives us this straight line. That is the vector 0.2 t, comma 0.3 t. Why would that be a straight line? Well, because that's the same thing as saying t times the vector 0.2, comma 0.3. So you get the vector 0.2, 0.3 with all the different scalings of that vector. You see, the t scales the vector, right? So let's suppose here's the vector in red. There is the vector 0.2, comma 0.3. Okay. R1 gives us all multiples of that vector. So you already know from a previous lecture that that's going to give you a straight line. 0.2, 0.3 is the direction vector of the line. Okay? All right, now let's look at the circle that's there. Whoops, I didn't mean to erase that. Let me write that part back in there. Okay. The circle, that's a different function. We'll call that one R2. And it is R2 of t equals cosine of t, comma sine of t. That's always going to give you a circle. That's the unit circle, in fact. Okay. Now, let's look at this picture. What do you think that graph is? Well, I don't expect you to guess. I mean, there's lots of things it could be. But let me tell you what it is. That is R1 plus R2 of t, which means R1 of t plus R2 of t. You see, think about it. If you want to add this line plus this circle, then what are you going to get? You're going to get something that moves linearly. Let's choose like a green or something. You're going to get something that moves linearly in this direction. And as it moves linearly, it's going to be also spinning around in a circle. And so what you get is you get that curly Q shape. Okay, now just a couple of other quick notions here. I want you to know what is called a displacement vector. Okay? If you have a vector valued function, let's just read along there, okay? Let r of t be a vector valued function, and let t naught be less than t1 be values in the domain. The displacement d, and what is d? Look, what's above it? An arrow is above it. So that means D is a vector, okay? So I would call it the displacement vector. The displacement D of vector R from t equals t naught to t equals t1 is simply r of t1 minus r of t naught. Now, let's make sense of this by showing you a picture. Let's look at that picture there. What's in the picture? What we have is we have this. R of t equals cosine of pi over 2t comma sine of pi over 2t on the interval from -1 to 1. Okay? And that's the blue semicircle. Okay? It goes from the point, well, first of all, let's say this. Why is it circular? Because it's cosine of something, comma, sine of the same thing. That's always going to give you a circle. Cosine of something, comma, sine of the same thing will always give you a circle. Okay? What's inside the cosine and the sine here is 1/2 t, and t goes from -1 to 1. So you're going to get a portion of a circle from the first point of the graph. Well, let me say this. The first vector is going to be cosine of -pi/2 sine of -pi/2. And the terminal point for that vector is right down here. Okay, so that's the point cosine of -pi/2 comma sine of -pi/2. I'm using parentheses because I've graphed the terminal point of the vector. I didn't actually graph the vector cosine of -pi/2 comma sine of -pi/2. Because you wouldn't see it because there's already a red vector drawn there. You see, if I were to draw that vector, it would go from here down to there, right? That's R1. I mean, sorry. That's R of -1 is that vector right there. Okay? But because it gets lost in the picture, because there's already a red vector that is already drawn in the picture, so instead I'm just plotting the point at the end of the vector r of -1. Okay? Now, r of +1 is going to end at this point up here. Cosine of pi/2 comma sine of pi/2. Okay? As you graph this vector valued function, you get a bunch of vectors that trace out that blue semicircle, and it does it in this direction, by the way, which is good to make a note of. Which direction does the semicircle get traced out? Okay, now, what is the red vector? The red vector is the displacement vector from r of -1 to r of 1. Okay? That red vector is the displacement vector from r of -1 to r of +1. And so that is the vector r of 1 minus r of negative 1. A vector minus a vector gives us a vector. And that's what that red vector is. That's the displacement from the beginning to the end. Okay, now I see that I should change my language slightly to agree with the red box. I said displacement vector from r of negative 1 to r of 1. But look at the wording that they used here. They say from t equals to t equals. So let me correct my language to agree with that. I would say it's the displacement vector from t equals negative 1 to t equals positive 1. Okay? And where is this going to come into play? Well, it comes in a lot when you're doing physics and you're tracing out a particle. Okay, let's pretend that the particle is whizzing around the paper, and its path is described by this function. Okay? Then the particle will follow the blue semicircle. But a lot of times, all you care about is how far away is the particle at the end from where it started. So in that case, so see what I'm saying? If you care about the actual path of the particle, then you would look at the blue graph of the vector valued function. But if you care about where's the particle located at the end compared to at the beginning, then in that case, you only care about the displacement from the beginning to the end, and that would be the red vector. Tells you that. It says, okay, the particle moved in a semicircular path, but what it did from beginning to end, if you just compare the beginning and the end, what you see is that the particle ended up at moving a point that is 2 units, that's the magnitude of that vector, 2 units in which direction? Up. Now it actually traveled more than 2 units because it went in a semicircular path. So it traveled more than 2 units, but its displacement from the beginning to the end is 2 units up. Okay, and then the last thing I want to show you, and I'm just going to show you the yellow box from the book, is called average rate of change. Okay, I'm just giving you a formula for it. Average rate of change from t0 to t1 is just the displacement from t0 to t1 divided by the length of the interval from t0 to t1. That's average rate of change. Okay, now we're not doing any calculus today. We'll start that in the next lecture.